Welcome back. Today we will solve a numerical example, and in particular we will solve an integro-differential equation that appears a lot in electric circuits, like for example RLC circuit. And the type of differential equation looks like this. We have the current, the derivative of the current itself, and the integral of the current in the circuit. So that's why it's an integral, because there is an integral differential equation, because there is also the derivative of the function. And of course, the unknown here is the function IT, the current in the circuit. This function here is the voltage. And for this very simple specific case, we are going to assume that L, R, and C, they are all equal to 1, the voltage is 1, and the initial current in the circuit is 0, okay? So let's try to solve this. Let's go to the blackboard and let's try to solve this problem. Now, we know how to solve this using the Laplace transform. So first, we transform the equation to the Laplace domain. That's the first step. And that means that the Laplace transform of the left-hand side in the equation, the left-hand side is this part, okay? I'm just copying the left-hand side. Now, the Laplace transform of the left-hand side must be equal to the Laplace transform of the right-hand side, which in this case is just the Laplace transform of the voltage. Okay? Now, I will substitute the values. L, R, and C are all equal to 1. So we can assume that these constants are equal to 1. Okay? And we know that the voltage is also a constant function equal to 1. So in the next step, we will apply these constant values, we will substitute the values, but also we will use the linearity property of the Laplace transform. And linearity means that the Laplace transform of all these terms is equal to the sum of the Laplace transform of each term. So the Laplace transform of I prime, the Laplace transform of IT, plus the Laplace transform of the integral term. So here we applied linearity, and we substituted L for the value 1, R with the value 1, and C with the value 1. At the right-hand side, it remains the Laplace transform of the constant function 1. Okay. Now, in the next step, we are going to use different properties. Let me make a bigger step, okay? Because we will use some properties, important properties. The first one is, how do we compute the Laplace transform of the derivative? Remember that we saw that if I have a function that is admissible, so it has a Laplace transform, then computing the derivative in time relates in the frequency domain to just multiply by s and subtract the value of the function at 0. That's what I'm going to use now. Okay, I'm going to use this property to compute the Laplace transform of I prime. That's going to be s times capital I of s, which is the Laplace transform of IT, minus the function at 0. Okay, so we used to compute the Laplace transform of the derivative, we used this property. Okay, now let's do the Laplace transform of IT. That's very simple because it's just notation what I'm going to use now. I decided to use this other notation, capital I of S, to denote the Laplace transform of IT. So at this step here, I'm also doing this change in notation and switching from this more complex notation, which is quite long to write because there are a lot of parentheses, and I'm switching to this other notation, which is much compact, okay? Now, the next term I need to compute is this term, okay? The Laplace transform of an integral. Now here we will use this other property, and it is that if I have a function that it has a Laplace transform, then when I compute the integral in time, then in the frequency domain, it means just dividing by s the Laplace transform of f. So that's what I'm going to use here. The Laplace transform of the integral term is just as simple as the Laplace transform of the function that is inside the integral divided by s. So I'm just using this property we wrote here. The only difference is that our function is not called f, but it's called I. That's the only difference. Okay, now we can continue with the right-hand side. This should be equal to the Laplace transform of 1. You can check that in your table of Laplace transforms, and you will see that for the constant function, its Laplace transform is 1 over s. So we know here, just using some table, we can check that this is 1 over s. Okay, so now I will use the initial condition of the problem. Remember that we know that at time 0, the current is equal to 0. So we know that this is 0. Okay? Now, this is very important. Right now, what we have is an algebraic equation. Okay, what I have here is an algebraic equation. This is not anymore an integro-differential equation because there are no integrals, no derivatives at all. It's just an algebraic equation where the unknown, okay, is this capital I-S. So what I'm going to do is to solve this equation isolating I-S, okay? So what I'm going to do is to take it common factor. This is s plus 1 over s equals 1 over s. In order to make it simpler, I'm going to multiply by s the whole equation. So I will get rid of the division here by s. So this would be s squared plus s plus 1 equals 1. And finally, I can isolate is, and it is equal to 1 over s squared plus s plus 1. And somehow, this is the solution to our problem. The only thing here is that this is a solution that is given in the frequency domain, in Laplace domain. And it's not very nice to have a problem given in the time domain and give the solution in the frequency domain. So there is the last step that is missing, and it's to compute the solution in time. I really want to know who is my current in time. Remember, I want to know the value of it. How can I compute that? Well, I need to use the inverse Laplace transform of capital I of s, and that's going to give me the value of the function in time, okay? So the last step in this problem is to compute the inverse Laplace transform of 1 over s squared plus s plus 1, okay? So let's try to do that. When we saw this type of problems in the other video lectures, what we did initially was to try to compute every time we had a rational function, we tried to use partial fraction decomposition, okay? And normally that's a good idea, but not in this case, because this is a very particular case where the denominator here has no real roots. So you can check that, but s squared plus s plus 1 has no real roots. Of course, it has complex roots, but not real ones. So it's not a good idea to try to find a partial fraction decomposition to compute the inverse Laplace transform when the denominator that we have is what we call irreducible. The meaning of irreducible is the fact that it has no real roots. Okay, what can we do? In this particular case, instead of using the partial fraction decomposition, what we use is called, as a technique, called complete the squares. Okay, so in the specific case where the denominator is irreducible, we will not use partial fraction decomposition, but we will use this other technique called complete the squares, which is quite simple. Let's do it with this particular example. The meaning of completing the square is to rewrite this expression as something similar to this. Let's write it like A here and B here. So the idea is to rewrite the expression that has no real roots as the sum of two squares. That's why it's called complete the squares, okay? And the idea here is that I need to find the value of A and B. Okay, how can I do that? It's like the idea of completing the squares the name is very nice because that's what I really do to find out who is A and who is B. I just write this the following way, okay? I don't write a specific value for A, but I try to guess. So if I try to do this operation, I will get S squared plus 2 times S times whatever I write here, yeah? And what I know is that S squared is correct because I have S squared here, but 2 times S is not nice. I want it to be S. So the only thing that it will work is to write here 1 over 2, because then this will simplify and I will get the S I need. So this term here should be 1 over 2. But if I continue with this operation, then I will get here plus, let me write it in the same color, and I will get here plus 1 over 4, yeah? And that's not completely right because I want here to have a 1, not 1 over 4. Okay, but don't worry, I still have this term to use, yeah? What do I need to write here? This extra term, what should it be? So these two will sum up and give me 1. Of course, this should be 3 over 4. 3 over 4. Or if you want, you can think 3 over 4 like the square root of 3 divided 2 squared. So the value of B would be this value, okay? So, summing up, we completed the squares for this specific example, and we obtained that it can be written as S plus 1/2 squared plus square root of 3 divided 2 squared. So this is the technique called complete the squares. And now we will see why it is very useful to compute the inverse Laplace transform of these type of functions. Let's do it with this specific example. So now what it remains to be done is to compute the inverse Laplace transform of 1 over, and we rewritten it like this, S plus 1/2 squared plus square root of 3 divided 2 squared. That's what remains to be done, okay? Now, what we will use here in order to compute this inverse Laplace transform is the following property that we saw in a previous lecture. it is a property that is called Sshift, or translation in frequency domain, and it looks like this. The meaning of this property is that if I have a function that it has a Laplace transform, so f of t has a Laplace transform called capital F of s, then if I make a translation in the frequency domain, a translation given by this minus a here, then what will happen in time domain is that the function will get multiplied by the exponential of at. Now you can see here that we have something pretty similar to that, because every s that appears in this function here, in fact there is only one s, okay, here we can see that this term s plus 1/2 squared can be viewed as s minus 1/2 squared. So it's like a shift in the frequency domain where the value of a that has been used is -1/2. So we can use this property, and what we have here is the function f of s minus 1/2 is this function f of s minus a. So its inverse Laplace transform is going to be the exponential of minus t/2 minus 1/2 t times f of t. But who is f of t? F of t is the inverse Laplace transform of the function without the shift. So I need to copy here the same function, but I will not have any more this shift. I will just write here s square plus whatever I had here. Okay, the shift as minus a, it's gone. Okay, now the only thing that remains to be computed now is the inverse Laplace transform of this term. And we can do that by looking into the table of Laplace transform. Let me write here that if you look into the table of Laplace transforms, you will have that given sinus function, then its Laplace transform looks like this: omega divided by s square plus omega square. Okay, and we can see that this function here looks pretty similar to this function here. Okay, so we will try to find out if this is a sinus function. Okay, I will try to do it here. The function that I really have is 1 over s square plus something that is already a square, which is the square root of 3 divided 2. So note here, this is square, it's already here. S square is already here. So this really looks a lot like a sinus. But I have a small problem, and the problem is that here I have omega, and omega is not here. If I had omega there, let me write it down. Let's suppose I have here omega. Okay, that's an assumption I'm doing. Then this will be very easy, yeah? Because I have omega, the square root of omega, as a square. This must be for sure the inverse Laplace transform must be for sure the sinus of this term. Okay, But that's not exactly the function that I wanted to compute its Laplace transform. I wanted a 1 here at the numerator and not this value. What can I do to arrange that? That's pretty easy because this is just a constant value. Remember that Laplace transform and inverse Laplace transform are linear functions. So I can multiply by any constant, and if I multiply in one side, it will instantly get multiplied in the other side because of the linearity. Yeah. So I can choose the value of c in order to rearrange the numerator, and instead of having this term, I want to have a 1. So what value of c will be choosing here? I will choose 2 divided square root of 3, which of course will appear here. And now this 2 will simplify with this one, and this square root will simplify with this one. And now the function I have here is exactly this function, the one that I wanted to compute its inverse Laplace transform, which happens to be this function here. So if I summarize, the function it, the solution of my problem, is the inverse Laplace transform of the capital IS. And capital IS was rewritten like this using the complete of squares technique. And we find out that the inverse Laplace transform is this exponential term times the inverse Laplace transform of this term, which happens to be this function here. So the final solution is that the current in our circuit will be given by this function we found here. This is the final solution to our problem. So that's it for today. Thank you very much. Bye-bye.